Hello, my name is Sergio Valentin, and today I'm presenting the paper Gun Model Classification based on fired cartridge case head images with Siamese networks. In short, this paper arose from a project that we're developing for the Portuguese Criminal Police, which is a automated ballistic identification system that aims to be able to identify the gun model that fired a given cartridge case head image. Here we can see the image of the base of a casing under the microscope, which is currently how the identification of a gun model is made over at the Portuguese police. Examiners have a particular cartridge under analysis, and then they manually compare the characteristics that are found in that cartridge to the characteristics that are found in another casings from various gun models, and then with this they cross this information and they cross these characteristics, and they try to find the most similar gun model to the one of the cartridge in analysis, and it's with this information that they then draw a conclusion about which gun model made the firing of that cartridge. This is a process all done manually, and it's a problem for the examiners because it's very time consuming. They have to compare many cartridges, and they have to be very well trained to know what is and what isn't relevant, and what is and what isn't similar. And at the end of this process, the the success rate is of only about 16%, so it's not very successful. In this short video, we can see how the firing mechanism of a gun works. We have the firing pin, which is what strikes the bullet casing, and it's at that moment that the projectile is fired from the casing, from the weapon. And because of that reaction, there's an opposite reaction that makes the mechanism recoil, and when the mechanism recoils, it brings the casing with it, and the casing is then expelled from the weapon. It's important to understand this because it's at this stage of the firing that the marks that allow for the identification of the gun model are imprinted in the casing. These are the parts I was talking about. So we have the ejector, which causes the ejection of the cartridge from the weapon, and the firing pin, which is what causes the bullet to be fired. And these are the marks that these components leave. We have the firing pin mark and the ejector mark. Both of them are very predominant in the casings, especially the firing pin, which is always present in the casing. And these marks can work like IDs, like fingerprints for each gun model, because every gun model will have slightly different parts, and each part is going to leave a slightly different imprint. So this is what we're relying on to be able to do this identification. So the objective for the research that we're doing is to be able to create a tool that will help examiners by, for example, giving them a list of the most likely weapons, or the most likely weapon models to have fired the cartridge that's under analysis. And with a tool like this, we would be able to standardize the procedure, because this is a procedure done manually, done by people, and there's always some subjectiveness associated with the process. So if we had a tool that was unbiased and that gave an unbiased look to the cartridges, then it would be able to standardize the procedure for the different examiners that do this process. And of course, that if the examiners had a tool to help them identifying the cartridges, we would be saving them time and optimizing their time spent. So the solution we came up with requires the use of scans that were acquired by the Portuguese criminal police, and that were then presented to us. And what we did with these cartridge scans was we segmented them into individual cartridges, and then we were able to build a data set with these individual cartridges. And this data set has 5 different classes, and each class represents a gun model. Um, but the problem we have with the data set is that it's somewhat limited, so we don't have many individual cartridges images, and it's imbalanced as well. As we can see here, we have a considerable higher amount of cartridges for the GT28 model compared to the other models. Another issue that we have is the fact that the unique firearms cannot be repeated between training set, test set, and validation set. So training set is used for the training of the network, and while the network is being trained, there's a validation set that validates the training accuracy, and at the end there's a testing set. So after the model is trained, we use the testing set to evaluate how well the model performed. And between these 3 sets, there cannot be repeated unique firearms. So because if that were to happen, it's likely that the network would be learning the unique firearm characteristics instead of the gun model characteristics, and it wouldn't be able to generalize to another models. So we use the Siamese neural network because the Siamese neural network is it's good for low amounts of data, because instead of classifying one single image, it's classifying actually pairs of images. So instead of us saying what the class of an image is, it's saying whether or not a pair of images belong to the same gun model or different gun models. And this allows us to make many pairs from a reduced amount of data. In this case, how a Siamese neural network works is we have 2 convolutional neural networks that are parallel and they are similar. At the end of each convolutional neural network, there's a feature vector that summarizes the input, and after these feature vectors, there's a distance function. What it does is it gets the output from those convolutional neural networks, so the feature vectors, and computes a distance. If the distance is low, it means that the pairs are from the same gun model, and if the distance is high, it means that they are from different gun models. Up until now, we've gotten some results regarding this Siamese neural network. If we use the whole cartridge case head image, so all the information we have on a single cartridge, we got a 51% accuracy, which, considering the context of the classification, which is binary, it's not a great result, because it's almost as if it's arbitrary. So you just say 1 or 0, and 50% of the times it gets it right. Then we used a bridge face, the bridge face for part of the cartridge, which yielded 51% accuracy as well. But then we tried using the firing pin impression, and that yielded a 70% accuracy result, which shows that this feature is a promising feature to feed into a network. What we see here is that there's a light cross in the firing pin, which we think that might be holding us back on the results, because this is not from the cartridge itself, it's from the process of acquiring the images. In the end, we also used the image binarization technique, but the results didn't improve. They in fact decreased the accuracy of the network. And at this point, this is what we've been working on, and I want to thank you all for your attention, and I hope you have a great day.